everybody. Thank you all for making it in at this early hour. Obviously morning people, so I appreciate the determination to get here. Today we're going to talk about streaming, database, and distributed systems, bridging this divide. So this is really a talk about stream processing and looking at it really from where stream processing has got to today, specifically this sub-branch of stream processing, which is known as stateful stream processing. And then we're going to have a look at how that can be applied to kind of more general problems rather than just streaming ones. So yes, this is me. I'm an engineer at Confluent, which is the company behind Apache Kafka, and I work on the team that builds the distributed log. So most stateful systems have to pull something from one of these three worlds. If you're in the business of building stateless systems, then you are very, very lucky, because stateless systems are nice, easy things to build in many ways, although quite a lot of them end up being stateless by really just pushing the state to somebody else's concern. But yeah, if you do that, then you're probably not going to find this very interesting. We'll be talking pretty much exclusively about the concept of stateful systems, which tend to have to pull these various different elements together. So the concept of a database, the concept of spreading state across a bunch of different machines and the communication that results from that, and then this idea of having event-driven systems. We don't always have to do polling. So today we have two goals. We want to understand stateful stream processing, sort of now and in the near future, and then we want to make a case, or I'd like to try and make a case for SSP being a more general framework for building data-centric systems. So data systems come in a bunch of different forms. Everyone's kind of probably familiar with the idea of a database. I'm sure everyone uses one. If you look at an OLTP database, so this could be Postgres, it could be Mongo to a certain extent. But the idea of a database is really focusing on a consistent view. So databases generally give you some concept of global consistency. But then the actual the internals are really designed to support updates and queries across individual tuples. So what that means is they're focusing on selectivity, the ability to take a large data set and narrow it down to something that's relatively small. So the tool that tends to be applied here is indexes. That's kind of what differentiates them. If we look at an analytical database, this could be something relational like Redshift, or it could be something like Spark. That's something that focuses effectively on aggregations, and it's going to do that via table scans. So you're typically optimizing for getting a large amount of data through a query engine. So there's a couple of kind of broad categories of databases. We can also think about messaging as being a data system. Jim Gray, who's an academic who's heard of Jim Gray? Yeah, we've got a few. So he once read a paper saying that all messaging systems essentially end up being databases. And this is because the contract of a messaging system actually ends up having to look a lot like a database, actually really like an OLTP database, because they have to provide this concept of selectivity. So if you have primitives like message selectors or routing keys in AMQP, you're actually introspecting a stream of messages in a very similar way to the way a database query works. But they tend to focus on limited state. So they tend to be relatively ephemeral. Distributed log is a different type of system. So Kafka, which I work on, is an example of a distributed log. Conceptually, it's very similar to a messaging system. So you have this idea, obviously, of state streaming through it with immutable records, but it builds in a couple of other concepts. So one is that the underlying structure means that you can retain data long term in a way that's much harder to do in a traditional messaging system. And actually that parallel is very similar to the difference between an OLTP database and an analytics database. Secondly, it also executes as a distributed system. So by being a distributed system, we have both the ability to scale out linearly as well as add in concepts of fault tolerance. So stream processing is this idea that we can manipulate concurrent streams of events. So it comes from a background in complex event processing, which has a pretty long history, dating about sort of 20 years or so. And in its core, it tends to be sort of ephemeral. So this idea that we have some machine, and we have a set of streams, and we're going to perform some computation inside this engine across these various different streams, and output something else. So stateful stream processing, which is this particular branch of stream processing, actually blends together a number of these concepts in one kind of product, as it were. So as such, it's a kind of a slightly more general framework for building these kind of systems. So what exactly is stream processing? Well, we can compare it back to a database, right? So if we think of like a typical OLTP database, will have these constructs. It will have data, and some data in a file and an index in a file, and those will be traversed by a query engine. Stream processing is a query engine, much like the query engine here, but it's something that's designed to operate over an infinite stream. So on the database size, it's a finite data set. Over here, it's designed for an infinite data set. And the thing about dealing with an infinite data set is that you have to bound that in some way. So that's why you bring in this concept of windows. So windows is a very simple idea. It's like we have these streams, and we're bringing them into this machine, which is going to do our computation. And all the window is really saying is, how many of these boxes am I going to allow into the machine at the point of time that I'm going to do the computation? So it's effectively, really, just a kind of buffering. So we have to put a window around our infinite streams to bound our computation. And this buffering allows us to basically, do a few things. It bounds our computation, but it also allows us to handle late events. So where we have infinite streams, a typical, in any particular problem that you apply this to, this data may or may not turn up when you want it to turn up. So if you're correlating 3 different streams, one stream might get held up, that system might be down, or it's from a mobile phone and the guy's gone into a tunnel, or whatever it might be. So you have to have this concept of dealing with late events, and that, again, is done effectively by buffering. So different stream processes have different sort of ways of describing this, but the concept's pretty much general. So what we're ending up with in stream processing is a continuously executing query. We have 2 streams of data coming in, some query, which is going to execute over some temporal window and emit results at some frequency. That's kind of the general approach. And what comes out is a derived stream of something else. So if we put something a little bit more concrete onto that, we might have a stream of orders and a stream of payments. And let's say we're some web company that has payments which are settled in different regions, and we're interested in how quickly those payments are settled across these different regions. So we take this average completion time across orders and payments with a group by emitting over a 1-day window and emitting every second. So we get this concept of completion time by region as a result. So that's kind of the basics of stream processing. Now, there's another concept that's a little bit like this. That's a materialized view in a database. Anyone use materialized views? Good. This is going to be much easier. So the materialized view is kind of interesting because a materialized view takes 2 tables, orders and payments, and takes this query and then physically manifest that as a separate table on disk, right? So we have a table now which represents the completion time by region. And actually, this query will be executed every time these tables change, by trigger, and materialize this materialized view. So why do we do this? Anyone have a go? Why do you use materialized views?
Performance.
For performance, exactly. So we're able to do this computation effectively real time, so that instead of every time a user does a query, we don't have to repeat this computation. It's already prepared for us inside this materialized view. So stateful stream processing is actually the process of creating materialized views. That's essentially what it is. So we can have, it's a little bit different because it blends these concepts of state, table, and stream. So we can have effectively a stream, a set of streams, and a table. So that the table is actually effectively a window, and a stream with an infinite window. And we can pull these in, we can perform this query, we can do an aggregate, we can do a join between these things, and then we can choose to materialize that view either as another stream, which somebody else can listen to, or as a tabular form, which a user can query. So you can see that with this sort of stateful construct, we have this ability to blend streams and tables, both as inputs to the computation, as well as the output pattern that we want. Do we want something that's going to continue to be streaming, or do we want something which is effectively an event store we can query? So one way to think about this is to think of a table as being a stream with an infinite window. In this case, it'll be a constantly updating table. So stateful stream processing is effectively about creating materialized views, materializing them either as a table or as another stream. So in its core, though, very similar to a database query engine, right? We can have the idea of streams. We have join operators, views, so you can translate things to your own internal data model, domain model, predicates, so we can do filtering, aggregate functions, etc. And then typically you can run these things over multiple machines. I guess that's unsurprising. But you can actually do that in 2 dimensions. So you can actually scale effectively in 2 dimensions. You can scale out horizontally by effectively spreading. So this is like sharding. So some subset of your data will be dealt with by this processor. Another subset will be dealt with by this processor. Which allows you to scale out horizontally. But you can also scale forwards by adding different levels to your chain. So you can actually end up with a kind of graph of processing which spans many machines. So stateful stream, so when you stream processing can use a brokered technology. I'm actually going to just jump to talking about brokered technologies. You don't have to use a brokered technology, and many stream processing engines don't. They implement things like backpressure to deal with some of the problems of overloading downstream nodes. But stateful stream processing engines pretty much always use a distributed log because they need the statefulness which they can inherit from that distributed log. So we need to kind of introduce this idea of a distributed log. And Kafka is an example of a distributed log. So this is a really, really simple idea. Like conceptually, it's almost so simple that it's hardly worth talking about. But you can literally just think of it as a file, right? It's just like a big distributed file. When you add messages, you add them to the end of the file. So new messages come on the end here. When you want to read a message, you have an idea of an offset within that conceptually distributed file. and you jump to the offset that you were last reading at, and you scan. So this has actually some pretty nice primitives in that it forces you to do sequential access effectively. As you probably know, that the sequential access is about at least 2 orders of magnitude faster than addressing things randomly, jumping around an address space or disk. Doesn't actually matter whether or not it's in memory or on disk. The performance difference is equivalent. And so by pushing you down this route of just doing sequential access, you end up with very efficient operations. So actually, Kafka is really just about reframing a problem such that it is only ever solved with sequential access. Actually, that's log structured merge trees are another implementation of the same kind of pattern. So the nice thing about this is you can where you decide to go from, whether you go from the start of the log or the end of the log, it doesn't really matter. It's effectively O of 1 for read, caching aside. So we have to introduce these other concepts. There's one more concept, and that's this idea of a compacted log. And this is the messaging system's way of representing a table, effectively. So if let's say we have a stream of orders, and you create an order, you might update the quantity of that order, and you might update your delivery address or something. You end up with 3 separate versions of the same order ID. If you represent those in a stream, you would have all versions, right? Because it's immutable messages. But you can have this, so that would be a topic in Kafka. You can also have this compacted log, and that's much like a database table. It will provide you with it will only keep the latest version for any key. So all of the versions that have been updated and replaced are effectively just thrown away. It's the latest key only. So we have this concept of a compacted log, and hence something which looks a bit like a table. So beyond that, the log is actually a distributed system. Inherently, a distributed log is, unsurprisingly, a distributed system. And that means that effectively we can have a bunch of different processes writing to it. We can actually have the distributed log itself spread over a number of machines with individual partitions, much like a distributed key value store. And then actually this bit's kind of cool. I'm not really going to go into it in that much detail, but you can actually then spread a single topic. This is really important from the perspective of data systems. You can take a single topic and you can spread the partitions which hold the data across a bunch of different machines. That doesn't sound that exciting until you actually think about what you need to do that. You actually need to be able to have the concept of leadership and leader election inside these reading processes. And the way that actually works is, the reason that you want to do that is so that you can survive failure. So these would effectively be, these could just be standard consumers reading messages, or they could be a stream processing engine. So if we get a failure here, we need to be able to reroute data to another machine. So what this ends up meaning is that there are actually 2 concepts of leader election. So there's 2 separate concepts of a leader. One which actually exists is private to the distributed log. That's how it deals internally with failure and recovery. And then there's another layer. There's another layer of clustering, another layer of leader election, which is inherited by anything which pulls data out of Kafka. So actually these processes will have, if you have multiple consumers, just regular consumers in a group, they will have, one of them will be a leader, and that's a protocol which is inherited from the distributed log itself. And if it fails, it will rebalance, data will rebalance, somebody else will become the leader, and a consumer actually has the ability to affect that, the result of what happens next. It actually has the ability to, the leader can spread the data anywhere he wants the data to go. So the log is important for stateful stream processing because it maintains this history. It acts a bit like a distributed file system and maintains history in a kind of push-based way. It has these primitives for an infinite immutable stream and a table. So it ends up being a little bit like a streaming engine. It is very much to a streaming engine what HDFS is to Hadoop. But it's a little bit more than that, because HDFS is just a file system, whereas here we're actually taking this concept of membership and inheriting it from the log. So these processes can be actually really simple and independent, and they're actually inheriting that concept of membership and what is effectively work distribution from the log without needing some external work manager process. So stateful stream processing is a bit different because it uses it's based on a stateful log. But there's a little bit more to it than that. Stateful stream processing engines also use a local key value store. So they actually have a database inside each of the stream processing engines. And this turns out to be quite important. This allows it to do a couple of different things. Firstly, it allows it to cache a stream we can cache a stream on disk. So this means effectively you can have very large retention windows, and that means that you can avoid the uncertainty that can come with late events. Secondly, you can actually cache tables. Remember, a table is just a stream with an infinite window. So you can actually, but it's actually a separate concept. So you can take a table, which you know if you ask a question of a table, you will always get a definitive answer, no matter how old that table is, because you're retaining an entire data set. So it allows you to take this concept of tables and cache them in the process with the stream processing engine. So there's a representation in the log, and then there's a cache of that inside each engine. In the case of a table, it's actually cached in its entirety. So this means you can do join operations between a stream and a table very efficiently within a single process. So here we have an example of an infinite stream coming from a distributed log through a stream processing engine, and we might do a very simple join operation between that and a table. So that might be, for example, a stream of orders, and this could be a table, an updating table that contains customer information. So this would be a very simple enrichment exercise where we're adding customers onto our orders. Now, that's still not quite enough, because if we're doing an aggregate computation, very simple sum, for example, we actually need some persistent state local to the engine, because this is actually a stateful computation. And if we fail in the middle of a window, then if we didn't have something that was tracking where we got to in that computation, then when we restarted, we might get a different answer. So you need the ability to basically persist your current value. And that, again, uses the key value store that's local to the engine. But as soon as you make that key value store read-write, right, you've got a problem. What happens if it fails? So the solution to that is that the key value store is actually backed up to the distributed log. So you end up with this process where you have effectively data in a distributed log, tables and streams cached in this layer, and then the ability to write intermediate state into what's called a state store, which will then flush that data back to the log so that it's it inherits all of the resiliency properties of the distributed log. So this allows us to do a few things which are kind of interesting, because it allows us to basically separate the concept of data, processing, and view. And remember, that view can either be another stream, or it could be a query, it could be something that's stateful, where we can execute a query and get the latest version. So if that might be, I don't know, a dashboard or something like that. So we can query these views from anywhere, or we can represent them as a stream. So what happens on failure? Well, we've talked about this idea of leadership. Because each engine's inheriting this concept of leadership from the log, the log will effectively cause this data to rebalance to another engine. But then even that can cause problems, because if this goes down, let's say this ends up caching a terabyte of data, it could take quite a long time for a terabyte of data to re-replicate to another machine. And we probably don't really want that. So one of the nice things you can do is, actually this just happens by default, is that the data will be pre-cached over here. So every time you make a stateful change, inside here, it'll effectively get replicated to another sort of hot processor, such that when a failure occurs, you can literally just switch membership over, wait for it to catch up, and then another processor can take over. So the result of this is that we get a couple of primitives for basically sharding and replication. So sharding and replication are sort of two primitives that you typically need to build a distributed database. Most distributed databases have primitives for that in some form. So we have this idea of processes, and they inherit a lot from the log. So we can just basically write something, a stream processing engine, which can then run as an independent unit, and we can inherit this idea of clustering. And this brings us to this idea of a slightly more general framework for doing distributed real-time computation. Now, unfortunately, there's a problem. The problem is correctness. If you've ever, who's built distributed systems with messaging? Does anyone, who does stream processing? I didn't ask this. Yeah, I know you do. So if you built, you all put your hands up pretty much. Everyone's built something with messaging. So when you use a messaging system, you always have this opportunity to create the duplicate data. And that's basically because it comes down to the two generals problem, essentially. So if you have, let's say we have a graph like this and we lost this particular node, we can fail that data across to another machine. But we don't have any way of guaranteeing, we can guarantee at least once delivery. We can guarantee that data will definitely make it across. But we can't guarantee that it'll only make it once. So that's when typically you'll implement this idea of idempotence. So idempotence is just deduplication. So we would have some deduplication process going on inside here. It actually turns out that deduplication isn't enough. Idempotence isn't a general solution to this problem. The general solution is to use transactions. Anyone ever used XA? Ooh, got one. Excellent. How was it? That's exactly what that was pretty much the answer I expected. So XA is like back in the days of messaging, you could basically chain together transactional resources like a transactional messaging system and a transactional database using an independent transactional manager. And this is sort of in the days of EJB when strange things happened. So you can do this in a slightly different way using this concept of distributed snapshots. And there's a few people who have done this, and there are a few flavors of doing it. Pretty much all of them are based on this paper by Chandri and Lamport about distributed snapshots. I'm not going to go into too much detail because it's reasonably complicated. We've had a guy working on it for a year. But actually, the broad concept's pretty simple. So the problem is you need to actually be able to transactionally ensure that data is not duplicated, but you also need to be able to do that across multiple streams. And effectively, the core concept's pretty simple. You have markers, much like you would in a database transaction. So you have these transactional markers, and you have a graph of computation, and you send the markers down the various different output streams, maintaining very clearly the offsets. So the nice thing about obviously the stream processing engine is everything has an offset, so you can kind of follow each stream according to its offset and then save a snapshot of the input that you got to. But then you actually need to emit that across multiple different streams in this sort of transactional way. So there's a bit which I omit from here, which is there is actually a transactional coordinator element, and that's really about the allocation of IDs. If you actually have your own IDs, you don't need to do that. But then effectively what happens is then each downstream processor has a buffer, and the buffer simply looks at these transactional markers and has rules to effectively obviously abort or commit. So basically only commit or proceed with a computation once it's received the commit marker. So it's really just this sort of concept of buffering and these various snapshot markers moving through a topology over time. Okay, so that was kind of like a load of stuff about stateful stream processing. So take a little pause at that point and ask the question, why did you just sit through all this stuff? Was there any point to it? Hopefully. So there's a few things that I think we can take from understanding or trying to understand this concept of stateful stream processing. So one is that we can posit that streaming is actually a superset of batch. So by batch processing, I mean historically, I guess it was done in relational databases and then made big by Hadoop, I guess. But so we can make an argument that says that streaming is a superset of batch because streaming obviously provides the ability to give you real-time computation, but it can also do historic computation. So databases are very much oriented around the idea of looking historically, looking back in time. This is actually pretty much just an act of the way they evolved, right? Like databases evolved around files, so they are inherently retrospective. But if we take something like an MPP batch engine, so you can think Hadoop or Redshift or whatever your flavor of choice is, and something like an MPP streaming system that's over a distributed log, batch is just streaming where you set the offset to 0. You just start from the start of the log every time. And actually, this is doing a table scan, right? This is basically table scanning across many machines. That's how an MPP batch system works. Whereas a distributed log is the same kind of concept, but it builds in this concept of being real time. So a streaming engine is really a superset of batch. It's not really strict. It's not a superset of a database because databases provide this concept of a global linearizable view, a linearizable concurrency model, which you don't get inside a stream processing engine, even with Chandra-Lamport. So that's kind of one concept. We have this idea that maybe there's a different way of thinking about data. Right? We can think about it in terms of taking streaming as being a superset of batch. There's another thing we can take from this, which is this idea of separating the store and the view. Okay, so this engine part is pretty lightweight, but it's stateful. Right? So it doesn't have any responsibilities for storage in itself, but it has this concept of state. And then there's a couple of things we can take from that. Firstly, we have this separation of concerns. So who's familiar with MVC as a pattern? Yeah, everyone, I would hope so. So you have this same kind of concept where we effectively have this model, view, and controller, and they're all effectively separate, and there's a physical separation here as well between those two layers. We can also think of this as CQRS. Who's familiar with that one? Yeah, great. I love this crowd. So, I mean, this is an implementation of CQRS, right? So you write to the model, your read store with its index is stored on a different machine and constantly updated, because really, as ever, we are creating this idea of materialized views. Streaming is all about creating materialized views. So it is really an implementation of CQRS. So if we go back to that original idea of a database being a query to a query engine with data and an index, we now have something that's kind of similar, where we have data, a query engine, which can be distributed, and then this idea of a localized view, which is effectively an index on a query. But we can manifest that view, obviously, as something we can query in real time, or something which we can distribute to another layer of processing in a kind of event-driven architecture. It's a third thing that we can take from this, which is that decentralized approaches are a little bit more general. So rather than pushing your processing inside an appliance, so remember, it's funny, over time, this idea of pushing code to data or data to code is kind of varied in terms of its kind of trendiness. I remember in the 90s, I worked with a guy who got very, very excited about the fact that you could put stored procedures in databases because they're really close to the data. And then that stopped being something that people did a bit later. And then, mid-2000s, there was data grids, which was about pushing code to the data, and then Hadoop, which is, again. So this idea of pushing data into an appliance is kind of attractive in some ways, but there's actually a distinct advantage to going the other way. So this idea of decentralizing your processing, pulling the data out into a set of different views. So this is what Martin Kleppmann would call turning the database inside out. Anyone seen Martin's talk on turning the database inside out? Yeah, it's a great talk. So this idea of taking a distributed log and decentralizing the processing into a set of independent views. So you can only do this if you can actually do fast data transport between machines and have the tools for caching these various different views in an efficient way, handling failure, etc. But this is actually a little bit more empowering because it's not focusing everything into a single appliance. And this isn't just about analytics, right? We can actually apply this to more general use cases. So what we're really thinking here is that it's more than just a database where we've added some push notifications. So whether you're looking at a sort of hulking great multi-stage streaming analytics platform where you have a series of intermediate views and a result store, you'd run queries, etc. Or at the other end of the spectrum, it's just a simple microservice application which wants to be able to blend these ideas of local state, shared state, and have the idea of hot instances, which is hot stateful instances. So we have this kind of whole range of different use cases that you can apply this to. And really, at its core, it's about composing these primitives. So query engine, primitives for replication and partitioning. And then the distributed systems concepts, membership and work distribution. So put it together, and we have this kind of potentially general framework for event-driven data computation. So you can go forth and build a streaming database that's just for you. That's kind of the idea. So if any of those ideas resonated with you, I'm really just repeating various ideas which other people have come up with. There's a bunch of information now. I'll put this up on the internet. So Pat Helland, Martin Kleppmann, These are a bunch of use cases. If you want to see how these things actually work in reality. Some of this is a bit more forward-thinking, and some of this is stuff people do now. As I said, some of these things are just evolving as we speak. But yeah, that's it for me. Anyone got any questions?
Hi, I had one question about the windows. In the initial example you had 2 timescales that you basically, it coughed out data every second and it was looking back over a day.
Yeah.
Now, I toyed with asking at the time, but I thought maybe you'll come to it later. Are those things kind of predefined, like, before you kick off the stream processor, you've defined those, or can you have a computation that says, oh, I might kind of look over a longer window or a shorter window depending on what's going on, or kind of I might cough out data when something's triggered? Or is it, basically that kind of there's an optimization there that says actually pick your windows first and then we'll work within them?
So, well, I think it depends on. So the answer is that it depends a bit on the implementation. I can only really talk about our
with your implementation.
Our implementation is actually relatively simple in this regard. And it's a good question. I mean, it's this whole space is kind of evolving. So at the moment, that parlance is actually really the kind of beam style parlance, and we don't have K-streams doesn't currently have a concept of triggers. So you're a little bit more limited in terms of your control of when things are emitted. But that's changing. So it's just, the background here is, so K-streams is a stateful stream processing engine. That's part of Kafka. It sort of comes in the distribution. It's just really a client of Kafka. There are others like Samza, which are a bit older and a bit more mature. But yeah, it's definitely something which is evolving. So yeah, the description here is general. It was relatively general, and actually I totally simplified. I actually merged the concept of windows and retention periods because. Well, actually, there's joins also have a concept of windowing, and I didn't really want to get into it because they're kind of the same. They kind of should be the same, sort of, but it gets a bit complicated if you try and explain all 3. Yeah. Any other questions? Does that sort of answer your question? Reasonably. Grab me at the end if you want to go.
Do you have any advice on maintaining like a complexity in a streaming system where different end consumers have different demands, which results in like different places in your architecture where you merge multiple streams into a separate stream, and then like how do you maintain oversight, and how do you do you have any ideas on that? Like what are good software engineering practices for maintaining a streaming system?
Yeah, so probably the best advice there is going to be a really obvious one, which is try and keep it simple. That's actually probably the one that doesn't necessarily get followed that well. There is significant complexity in this. There is the ability, I'm not going to do that saying about power and stuff, but obviously you have a lot of rope here which you could really hang yourself with if you wanted to. That's kind of the nice thing about having a sort of appliance where you just ask it to do a job and it does it and it returns, is that you have really not that many options well, you don't have as much lateral room to maneuver. So yeah, there's a lot of opportunity to kind of get this wrong. So I think the core thing is really just to try and keep these things simple. Don't, for example, if you can, don't use a multi-stage topology, which you can do in a lot of use cases don't require a multi-stage topology. That's actually a lot simpler. You can, inside K-streams, you don't have to, so you have the option of basically chaining together different operations, and you can choose whether or not those go out of the process space or not. So either they go back into Kafka or not. And it's generally simpler if you can just sort of bound your problem so that it is either one node or just one set of nodes that scale horizontally. That kind of keeps things simple. Other than that, actually the reality, there's a reality which is that any database, when you build something that looks like a database, you actually get all the problems that then will result from having a database. So anything that you can imagine a DBA doing, you will end up having to do in this system that you build. That's actually the reality of it. So things like you will end up worrying about schemas and schema migration and what happens when data gets old and how do I get a snapshot of data into my development environment so I can get a reproducible result, and it's all those kind of things. So yeah, these things are definitely actually the simplest thing to do. Is just the best thing to do is just to keep it simple. That's probably the best advice I've got. Yes.
Hey, what tools are there available for managing and optimizing a kind of streaming framework? Is there anything available really for actually just managing this distributed system for you and coming up with, say, an optimal setup?
Not that I know of, no. Certainly isn't anything for K-streams. There might be something in, well, yeah, maybe Storm. No. It's a good idea, though. Maybe you should build one. I think that sounds like a very useful tool. At the moment, this stuff's pretty raw, is the truth.
What real-world uses is this being put to? You mean you hinted at analytics for orders, but where is it being used in the real world? And are there any places where it's working really well or really badly? If you can talk about the latter.
So K-streams itself is actually only about six months old, a bit older than that. So although there's a lot of activity, there's actually probably about as much activity on the user group about K-streams as there is about Kafka, and Kafka's got a pretty big user base. The most of the use cases are actually relatively simple. So you see a lot of people kind of dipping their toes into this with simple enrichment exercises. So I guess just like that, just that idea of blending a stream and a table. And actually, for what it's worth, there's another feature that's coming in which is really important for that type of use case, which is more of a sort of businessy use case, which is to be able to do a multi-join. At the moment, you can only ever join, we didn't really talk about this, but you can only ever join 2 streams. The reason for that is that you have to shard the streams with the same key. So you actually end up one of the things that you end up doing is rekeying data sets so that you can get them on the right key for the join, because each partition has to be the join key for the partition. The partitions have to be co-located. Anyway, there's a kind of more general framework for doing that, which is about replicating tables across different stream processing engines, which is coming out shortly. But yeah, most of the use cases are either that I've seen, or they're more sort of classical streaming systems. So that's analysis of click streams, like normally things which result in aggregate values. So things that end up on like a dashboard. So this is my sales conversion rate for this particular product, that kind of thing. But yeah, it's still relatively new. But streaming's obviously been around a while.
Well, all right, I think we're out of time, so we'll have to thank Ben again. And
Thanks very much.